Welcome to my course on electromagnetism. This course is primarily intended for the second semester students of Bengaluru City University who have offered physics as one of their discipline core subject as per the new education policy 2020 or NEP 2020 rolled out by the government of India and adopted by government of Karnataka in 2021. I am Professor K.M. Raghavendran, formerly the head of the Department of Physics, MES College of Arts, Commerce and Science, Malleshwaram, Bengaluru. This course presupposes that students are exposed to the basics of electricity and magnetism at the level of class 12 of the CBSE or ICSE Board of India or the pre-university course offered by the state of Karnataka. An exposure to the fundamentals of differential and integral calculus at the level of grade 12 is desirable but not essential. The course is divided into three parts. Each part will have a set of lectures of about 90-minute duration or less. Part 1 will consist of two lectures in which I will cover the mathematical tools required to study and understand electromagnetism. Part 2 of the course, which is the core of the course, will consist of 5 to 6 lectures in which we will cover the basics of electromagnetic theory, including setting up of Maxwell's equation, the mathematical description of an electromagnetic wave, and energy transported by an electromagnetic wave, the idea of Poynting vector, etc. This will also include some problem sessions. The third part will consist of a set of 3 lectures in which I will cover a set of assorted topics like the magnetic moment associated with an electron, the magnetic moment of a point charge moving in a circular loop, the electric current associated with atoms, and so on. The course will have 3 problem solving sessions, 4 quizzes, and 3 assignment sets. There will be one final examination on the entire course in the end. The mathematical framework of electromagnetism or electromagnetic theory was put together by James Clerk Maxwell in the late 19th century, and this theory has remained one of the pillars of physics over the last 200 plus years. This slide shows the entire electromagnetic spectrum as we know it now and the broad areas of their application. Note how important electromagnetic waves are in these modern times. Radio waves, which are among the electromagnetic waves with the largest wavelengths, are used in television and radio broadcasting, and as you go to higher and higher frequencies or lower wavelengths, the other end of the spectrum is gamma rays, which are essentially used in radiation medicine, cancer therapy, and so on. Now, in this lecture, I am going to focus primarily on some of the basic definitions and mathematical tools that are required to study and understand electromagnetic theory. Now, let us start with the idea of what is a scalar field, and then we will move over to the idea of a vector field, and then I will introduce the most important vector differential operator that will be used extensively in my course, namely the nebula or the del operator. Let us start with the scalar field. Physics, as you know, deals with physical quantities. Now, these are quantities that are measurable and quantifiable. There are two main kinds of physical quantity, scalar quantities and vector quantities. A scalar quantity is one which has a magnitude but no direction. Quantities such as temperature, density, speed, distance, electric potential, etc. are classic examples of scalar quantities. Now it turns out that if the value of a scalar quantity is a function of x, y, z at a point in space, then we call such a function as a scalar point function. If in a region of space R, we associate a scalar point function with each point in that space, then the entire space or region is referred to as a scalar field. The figure here shows a schematic representation of a scalar field, which is essentially a temperature field. In this region, we note that each point has a specific temperature and there are certain regions where the temperature is constant. However, different regions have different temperatures. The color that you see, different colors, represent regions of different temperatures. So this kind of a field is called a scalar field. Let's now look at the concept of a vector field, a physical quantity that is completely described by magnitude and a sense of direction is called a vector quantity. Typical vector quantities include displacement, velocity, acceleration, and so on. In the context of electromagnetism, electric intensity and magnetic intensity are two important vectors that we will come across. Now, if you have a vector which is a function of the space coordinates x, y, z in a region of space, then that function is referred to as a vector point function. A vector is generally represented by a directed line segment with an arrow. The arrow indicates the direction of the vector. Now, if in a given region of space R, we associate a vector point function with each point x, y, z of that space, then the entire space is referred to as a vector field. The velocity distribution in a fluid, the gravitational field around a mass distribution, the electric intensity around a charge distribution, or even an isolated charge are typical examples of vector field that we will encounter. The slide shows the electric field, which is a vector field, around two identical charges. These are two equal positive charges, as well as the electric field around an electric dipole. A dipole, you will recall, is a system of two equal and opposite charges. One looks at this field and we note that in the schematic representation, we have used the concept of field lines. These lines indicate the direction and magnitude of the field. The regions where these lines are crowded are regions where the electric intensity is large, while the regions where these lines are spaced out further are regions of lower electric intensity. Coming to the direction, the arrows on these field lines indicate the direction of the electric intensity at these points. More specifically, if a field line is curved, then at any point on this curved field line, the tangent drawn at that point would indicate the direction of the electric intensity at that point. Typically, it is assumed that the electric intensity vectors are directed from the positive charge to the negative charge. Now, in order to learn electromagnetism in a very, at least in an elementary manner, it is important to understand the concept of the vector differential operator called nebula or del. The vector differential operator del was introduced by Sir William Hamilton. In Cartesian coordinates, we write the operator as del equal to dou by dou x I cap plus dou by dou y j cap plus dou by dou z z cap, where I cap, j cap and z cap are unit vectors along the three x, y and z directions in the Cartesian coordinate system. Now it turns out that the del vector or the del operator, as it were, can operate on a scalar point function or a vector point function. In the next slides that follow, we will define these fundamental operations of the del operator on a scalar point function, which is defined in a scalar field, and a vector point function which is defined in a vector field. Now, when it comes to a scalar field or a scalar point function, the operation of the del vector, or rather the del operator I should say, on the scalar function gives rise to what is known as gradient of the scalar function. So the del operator operating on a scalar function gives rise to what is called the gradient of that function. We will see in the next slide what gradient really means and how one can calculate the gradient of the scalar function. On the other hand, the del vector or rather the del operator can also operate on a vector field or rather a vector point function. There are two ways in which the del operator can operate on a vector function, as we will see. Let us begin with the gradient of a scalar quantity or rather scalar point function. Now suppose I consider a scalar point function psi xyz in some region of space. In this region, let us consider two surfaces which are called as laminar surfaces. Now essentially what happens is, in a scalar field there are regions, or rather I would say surfaces, over which the value of the scalar function is a constant. Such surfaces are also called as level surfaces. So let us consider two level surfaces here. One, a surface 1 on which the scalar point function has a value, let us say psi, and then there is another level surface certain distance away from the first level surface. Let's call this level surface 2, in which the scalar function has a value psi plus delta phi. Now obviously when you move from the level surface 1 to level surface 2, the value of the scalar function or scalar point function has changed, and it has changed by an amount d phi. However, when one asks this question, what is the rate of change of this scalar function as you move from the first level surface to the level surface, to the second level surface? It turns out that the rate of change of phi from one surface to another surface at a point depends on the direction in which we move from surface 1 to surface 2. So the whole point we are trying to tell here is that if d phi represents the change in the scalar point function when we move from surface 1 to surface 2, d phi by dr, which basically represents the rate of change of phi going from surface 1 to surface 2, depends on the direction along which we move. So if I consider a point P here on the level surface 1, and I want to go from P say to the point Q or P to the point R, which are in different directions, the rate of change of phi from level surface 1 to level surface 2 along PR will be different from the rate of change of phi along Q. That is the most important point you need to understand. I'll repeat that again. The rate of change of phi along the direction PQ will be different from the rate of change of phi along the direction PR. Now it turns out that the maximum rate of change of phi is found in a particular direction and is a vector. The magnitude of this vector is dou phi by dou n, where n cap is the unit vector normal to the surface or level 1 at the point P. This maximum rate of change of phi at the point P is known as the gradient of the scalar quantity phi at P. Since the rate of change of phi depends on the direction, the rate of change of phi, or rather the gradient of phi, is taken as a vector. Now it can be shown that this maximum rate of change d phi by dn along the direction n cap, which is shown here, is nothing but the differential operator, vector differential operator del operating on the scalar function phi. In other words, it can be shown that grad phi, that's how this is read, grad phi is nothing but I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. I'm sure that you all understand that this dou by dou x of phi represents the partial derivative of phi with respect to x. That means dou phi by dou x basically means the derivative of phi with respect to x. If phi is in general a function of x, y and z, then when you differentiate phi with respect to z, we treat y and z as constant in evaluating dou phi by dou x. Similarly, dou phi by dou y represents the partial derivative of phi with respect to y, and so on. Dou phi by dou z is the partial derivative of phi with respect to z. Now here is an example to elaborate my point. Let's consider a scalar function phi, which is x squared y plus 2xz, and let's say I want to evaluate the gradient of the scalar function at the point 2 comma 1 comma minus 1. That means in a given region of space at a point P whose x coordinate is 2, y coordinate is y, and z coordinate is minus 1, I want to evaluate what is the gradient of this function. Notice that this is a scalar function. How do you differentiate a scalar function from a vector function? If a function does not have I, j, k in its mathematical expression, it would be a scalar function. So what do I do to calculate the gradient? All that I need to do is operate del on this function psi and evaluate the corresponding value at 2 comma 1 comma minus 1. So therefore I do that. Del is nothing but I cap dou phi by dou x. So when I operate it on psi, it becomes I cap dou psi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. And I have to evaluate this and find its value at 2 comma 1 comma minus 1. So let's do that. When I substitute for phi as x squared y plus 2xy, I easily see that dou by dou x of x squared y plus 2xy is nothing but 2xy plus 2y. You differentiate this expression in the numerator with respect to x. So the differential coefficient of x squared is 2x, and in this product you treat y as constant, and hence you have y there. And in the second term 2xy, the differential coefficient with respect to x would be 2y. Similarly, I differentiate the same function with respect to y here and the same function with respect to z here. Notice that in the third derivative, since the function does not have z, x and y are treated as constant, and obviously the derivatives of constant are 0. So finally, I end up with the following result, that the gradient of this function phi is basically 6i plus 8j plus 0k. From where did I get 6, 8 and 0? I just substituted the value of x, y and z because we need to calculate this gradient at the point x equal to 2, y equal to 1, z equal to minus 1. So when I substitute in this expression x, y and z values as 2, 1 and minus 1 respectively, I get this. The point I would like to draw your attention to is that our function psi was actually a scalar function. But the moment I operated the del operator on it, the gradient of this function, notice, is a vector. Now incidentally, this vector represents the maximum rate of change of phi at this particular point. The direction of this vector will give you the direction of that maximum rate of change, and the magnitude of this vector will give you what is the magnitude of the maximum rate of change. The magnitude of any vector which is xi plus yj plus zk is root of x squared plus y squared plus z squared, and therefore the magnitude of gradient or rather the magnitude of the gradient of this function is root of 6 squared plus 8 squared plus 0 squared, or 10 units. Now there are some useful results which you need to memorize and also prove. I leave it to you as an exercise. Now if you consider any point in a three-dimensional space in Cartesian coordinates, the position vector of that point from the origin is represented by this vector r, which is xi plus yj plus zk. The modulus of this vector is root of x squared plus y squared plus z squared. It turns out that these are some useful results which will be which you can prove yourself. It's rather simple, and I leave it as a small exercise for you to do. For instance, when you take the gradient of r, notice that vector r is a position vector, it's a vector, but the magnitude of this position vector is a scalar. So I can operate the del operator on this scalar quantity to get what is called grad r. So grad r here happens to be the vector r itself. I want you to check this out by using the definition of the gradient of a scalar point function. Interestingly, there is one direct application of these results. Now, in the concept of when you look at the electric field around an isolated charge, at any point in the electric field, one can define an electric intensity, which is a vector, and one can also define something called the electric potential. Now, it can be shown that the negative of the gradient of the electric potential of an isolated charge, or for that matter at any point in an electric field, the negative of the gradient of the potential at that point is nothing but the electric intensity at that point. So this last result here where V is the electric potential. Let us say you consider an isolated charge and V becomes the electric potential at a point due to that isolated charge, then the negative of the gradient of the potential can be shown to be equal to the electric intensity at this point. I urge all of you to work this out. I leave it to you as an exercise to figure out what is the function potential, what is the expression for potential due to an isolated charge, okay, at a point x, y, z in the Cartesian coordinates in any space, right? And what is the expression for electric intensity at the same point due to an isolated charge? And then if you apply the rule of gradient and calculate the gradient of the potential and multiply that answer by -1, you will find that the result is nothing but the electric intensity. Having said all this, I would like to highlight a few points which you have to remember in the context of this gradient. Now we noted that the gradient of a scalar function is a vector. However, it does not mean or does not follow that any vector point function can, or rather a vector field can be represented as the gradient of a scalar point function or a scalar field. In order for a vector point function or a vector field to be expressed as the gradient of a scalar point function or a scalar field, there is a certain condition to be satisfied. This condition can be stated in two different ways. One way of stating the condition for a vector field to be expressed as the gradient of a scalar field is that the line integral of the vector field or the vector taken between any 2 points in the vector field should be independent of the path along which that line integral is evaluated. And further, the value of the line integral should be the difference between the values of the vector point function between the 2 points uh, between which you are calculating the line integral. In fact, any vector field that can be expressed as the gradient of a scalar field is sometimes also referred to as a conservative field. Now, alternately, a vector point function or a vector field can be expressed as the gradient of a scalar point function if the line integral of the vector field or a vector taken over any closed path. That means you start at point 1, evaluate the line integral and come back to the same point. So if the line integral of the vector field or vector over any closed path is 0, then such vector fields can always be expressed as the gradient of a scalar field. Incidentally, there is a name for this. Any vector field that can be expressed as the gradient of a scalar field is known as laminar fields. Such a vector field can be divided into layers or laminae or level surfaces over which the corresponding scalar quantity will be constant. We referred to this when we talked about the scalar field level surface 1 having psi and level surface 2 having psi plus delta psi. Now the second kind of operation that the del operator can operate on is on a vector. Now before we understand the operation of the nebula operator or del operator on vector, it's very important to understand the concept of flux in a vector field. Now suppose I consider a vector field A and let A x y z be the value of the vector point function at some point P x y z in the field. Now we define the flux of the vector field at this point P as the dot product of the vector A at that point and the vector ds, where ds is an infinitesimal area around the point. Now some of you may be wondering, how can I treat an area as a vector? Now this is a very important construct in mathematics, particularly in electromagnetism. It turns out that when I have an area around a point and I put that area in a vector field or a scalar field, I can orient that area in different directions. And when I orient it in different directions, as you will see later, particularly when I orient an area in a vector field at a point in different directions, the quantity called flux that passes through this area will be different. So one treats the area, or rather one can treat an area mathematically around a point as a vector. The magnitude of that area will be the value of the area itself. The direction of the area is taken as a along the direction of unit vector which is drawn perpendicular to the area. So for example, if you consider this blue area here, the value of the area is the magnitude of the vector area ds. The direction of this vector ds is along the normal to this area. So the moment I consider ds as an area whose direction is along this normal, and a is the vector point function at this point P, in general these two need not be in the same direction. There would be some angle d theta between them. Now when we talk of flux passing through this area, it refers to the mathematical construct of A dot ds. So therefore the flux of a vector field at the point P xyz is defined as vector A dot vector ds, where ds is an infinitesimal area around the point P. As I already mentioned, treating ds as a vector, the magnitude of which is equal to the magnitude of the area and whose direction is normal to the area. Thus, flux of area A is a scalar. That's an important point to remember. The flux of vector A would be scalar because the dot product of any two vectors is basically a scalar. And incidentally, from elementary mathematics, you would have known that the dot product of A and ds is nothing but mod A into mod ds into cosine of the angle theta between them, in this case d theta. So A ds cos theta. That is flux. Now, this concept of flux is used to define what is known as the divergence of a vector field. Now, for instance, suppose I consider an infinitesimal volume around the point P. Let's say I have a point here, and I'll choose a pen. Let's say I have a point here P, and around this let me consider a certain volume dV, or you may even write it as delta V. So if you consider this infinitesimal volume delta V around the point P, you will notice that this volume is bounded by a surface S. I suppose you understand what I mean by the surface S bounding a volume. Let's imagine a football. If you take a point at the center of the football, the surface of the football is actually the bounding surface, and the volume of the ball is the volume that is around this point P, which is the center of the football. So let S be the surface which bounds the volume. Now one can talk of what is the total flux. Of course, this whole thing is in some vector field. So you have some vector field A, and in that vector field I have a point P, and around that point P I am considering a certain infinitesimal volume delta V, which is bound by a certain surface S. Now what I can do is I can calculate the total flux that crosses this surface. How do I do that? Literally I would divide this entire surface into large number of small surfaces ds. I will calculate the flux across each of this ds, which is basically the value of A at that point dot with ds at that point. I get this A dot ds. Like this, I can calculate this A dot ds across many such ds across. I will divide the entire surface S into large number of ds, calculate the flux across each surface, and sum them all up. This whole procedure mathematically is nothing but integral of this quantity A dot ds taken over the entire surface. Incidentally, this would be a double integral. So this quantity represents the total flux that crosses this entire surface S, or rather the total flux that comes out of this volume, or even it could even be going into the volume, as I will explain later. So basically, what is this integral A dot ds over the entire surface? Yes, it is nothing but the total flux across this volume. Now we define the divergence. This is the definition. We define the divergence. Let me use a pointer now, so that it will be easy for me to explain to you. We define divergence of this vector A as this quantity integral A dot ds over the entire surface divided by delta V, the value of this quantity in the limit when delta V tends to 0. So we can say the divergence of the vector field at the point P is nothing but limit of integral A dot ds over the surface divided by delta V in the limit when delta V tends to 0. This integration is carried out over the surface of the infinitesimal volume dV that shrinks to a point. That's the whole idea. So basically one looks at the divergence as the numerator here is nothing but the flux across the entire surface. Delta V is the volume that is around this point P, and therefore this term in the bracket here is nothing but flux per unit volume. So the bottom line is this: the divergence of any vector field at any point P in the field is nothing but the flux per unit volume that crosses an infinitesimal volume around that point. And that's what is written in the last sentence. The divergence at a point is the flux per unit volume that crosses an infinitesimal volume around that point, in the limit when the volume tends to 0. The question that would come in your mind is, how do we actually calculate this? And that is what the next slide shows. It can be shown that, and this will be done in your class in detail, you can look up any textbooks of electromagnetism which will prove this to you, and I urge you to do it yourself. It's quite simple. Divergence of A, vector field A or vector function A, which is already defined like this, can be shown to be equal to dou by dou x of Ax plus dou by dou y of Ay plus dou by dou z of Az. What is Ax, Ay, Az? Ax, Ay, Az are nothing but the components of this vector A at this point P, X, Y, Z. Now if you observe this carefully, dou by dou x of Ax plus dou by dou y of Ay plus dou by dou z of Az, this is a scalar quantity. This is a scalar quantity. So how do we arrive at this? And that is where one has to appreciate, or rather really understand how vector calculus is so useful in describing physical situations. Now consider the dot product between the del operator, the nebula operator, which was, if you recall, what was the del operator? I think you will all remember what the del operator was. Let me write it out for you. The del operator was essentially I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. So that's a del operator. And if you take the dot product of this del operator with our vector A, that is del dot A, then lo and behold, the answer is dou by dou x of Ax plus dou by dou y of Ay plus dou by dou z of Az. And that's precisely what we defined as divergence of A. And therefore we get this result that when we operate the del operator on a vector point function through the dot product, then we get what is called the divergence of the vector field. Let me go back to the pointer so that it will be easy for me to explain to you. So the divergence of A is nothing but del dot A. The point to understand here is A is a vector field, but if you take the divergence of that field, you get a quantity which is nothing but the net flux, and that is nothing but a scalar quantity. Now there can be two possible scenarios here. When you calculate this net flux across the volume that we are talking of, the answer may be positive, algebraically positive. So what does that mean? A positive value of divergence implies that flux is emerging out of the volume. Now what do I mean by flux emerging out of the volume? Again, I think I would do a very schematic diagram for you. If I have a positive charge, we know that the field lines are supposed to be emerging out or move outwards from the positive charge. So if I consider, for example, a certain volume around this charge, then when you calculate the flux across this volume, you will notice that the flux is going to be positive. That means this answer is going to be positive. That would mean that this volume is enclosing a positive charge. A positive charge can be thought of as a source of an electric field because lines of field emerge from it. On the other hand, if you take a negative charge, the field lines actually terminate on a negative charge. These are elementary things you would have learnt in second PUC. So you have these field lines terminating on the negative charge, and if you consider a certain volume around it and calculate the flux, you will find that the net flux is actually negative. A negative flux implies that flux lines are going into the volume, and when flux lines go into the volume, it is as if you have a sink inside that volume. So therefore, a negative value of divergence implies flux is flowing into the volume, which means that the volume contains a sink in the field. Now there could be situations where you have a vector field where you take a certain volume and you find that the flux across that volume is zero. So what would that mean? That has two implications. It could imply that inside that volume, that is, if the divergence across a certain volume in a vector field is zero, it could imply that within that volume you neither have sources of the field nor you have sinks of the field. That's one possibility. Or it could mean you have equal number of sources and sinks of same strength. Okay, so such fields in which at any point in the field the divergence is zero are called as solenoidal fields. So if del dot A is zero, where A is a vector, then this should be a vector. Then it means that if del dot A is zero everywhere within that vector field A, we would say that such a field is solenoidal. The last and probably a little easier concept to understand, but it is quite abstract in one sense, but easy to understand in a different sense, is the third operation of the del vector or nebula vector on a vector field. We already saw how the operation of the del vector through a dot product on a vector field gives you a scalar quantity, namely the flux of the field. Now, what if you can operate the del vector on the vector point function through a cross product? You all know from your elementary classes of class 12 that between two vectors you can have a dot product or you can have a cross product. Well, the cross product of del taken with a vector point function gives rise to another operation called curl of a vector field. To understand this, let's first look at an analogy. Let me read this slide first and then go to the analogy. Maybe a pointer will be of some use here, so I will choose a pointer now. The cross product of nebula or del operator with the vector v is known as curl of the vector field. Now geometrically, the curl of a vector field at a point is a measure of how much the vector v curls around the point under consideration. So how much does it curl around that point? It is going to be a little abstract to understand this concept of curl without an analogy. We will later come to the point where we tell you how to calculate it. Well, here is a simple analogy. Suppose I am standing, say by the edge of a river where water is flowing, and if I were to float a small paddle wheel here, maybe a cork which has a lot of needles stuck into it, and I drop this at a certain point P in this river where water is flowing, let's say, and then I see that this paddle wheel starts turning at that point. For a moment, imagine this: water is flowing. This paddle is not moving along with water. Let us say it starts swirling there. So if the paddle wheel starts swirling there, then I would say there is a curl of the velocity field at that point. Now in this case, what is the vector field in this water that's flowing? The vector field we are referring to is basically the velocity field, because at every point the water will have a certain velocity, and velocity is a vector. So we would say that if this particular object, this paddle wheel, starts revolving or rotating at that point, then I would say in this velocity field at that point there is a non-zero curl, or there exists a curl. Suppose this paddle wheel does not rotate. Suppose this paddle wheel does not rotate, let us say. Then what happens? We say the curl at that point is zero, right? So in this case, of course, it was a very simple analogy. Now going to the mathematics part of it, there are more general ways of defining a curl. You see, this requires you to understand once again the concept of orientation of a certain area in the field. To understand the general definition of curl, we do the following. Now let's say you have a vector field. Let's say you have some vector field like this, and in that vector field I'm going to place a certain area. Now this area can be placed in different orientation. This is orientation number 1, and maybe I can think of another orientation here like this. You see, since the normal to the area is in a different direction, this orientation is different from this orientation. Now when you place a certain area like this area is around this point P, there is a curve that bounds that area, and one can calculate what is called the line integral one can calculate the line integral of this vector. Suppose this vector field is V vector. I can calculate the line integral of this vector bounding this area. So V dot dl is basically at this point. Suppose I take a very small curve here of length dl, and the normal to that surface and this vector v will have some angle. So I can calculate what is v dot dl at that point. Similarly, I can do it for different dls bounding the curve, add them all up, and that mathematically would be what's called the line integral. So if I calculate this line integral, it turns out that the value of this line integral depends on what orientation the area is. First, get this right. We are looking at a certain vector field. In a vector field, I have this point P here, and I could keep an area around it, bounding this point P, and this area is bounded by a curve, and I can calculate this integral bounding that curve. The value of this integral will depend on how I keep that area, orient that area. Okay, so that's what I mean here in the first bullet point. I say if we place a small area, so let me go back to the pointer option, which is easier for me to explain to you. If we place a small area of any shape in a vector field and compute the line integral of the vector v around its boundary, and the boundary is this, it turns out there will be one orientation of the area for which the value of this line integral is maximum. That means if I calculate integral v dl for this area, which is oriented in this position, the same area kept at the same point, but say kept like this integral will have a different value. That's what we're trying to say. So if we place a small area of any shape in a vector field and compute the line integral of that vector v around its boundary, then there will be one orientation of the area for which the value of this line integral will be maximum. Now, in that orientation, if we calculate the line integral, that is, we get the maximum value of the line integral, and you divide that maximum value of the line integral by the area itself, then that quantity, namely integral v dot dl, rather the maximum value of integral v dot dl divided by ds, gives rise to a quantity which is called curl of that vector field at that particular point. So this is the definition. The value of this maximum line integral divided by the area is called curl of the vector field at that point. Now, since the line integral itself depends on the orientation, one thinks of the line integral as a vector, because the value of this v dot dl, integral v dot dl here in this orientation is going to be different from integral v dot dl at the same point if the area was kept like this. For clarity, I have drawn this area separately, but you could imagine the same area kept here, then the orientation of this area is different from the orientation of this area at the same point. So therefore, the curl of the vector field mathematically is basically integral v dot dl taken over the entire bounding line or curve divided by ds when this integral is maximum. So it turns out that in order to do this evaluation, all that we have to do is take the cross product of the vector field v at that point with the del operator. So if you do del cross v, what we get is this, and that is the magnitude of the curl. The direction of the curl obviously will be the direction of the normal to the area at that point when we evaluate this del cross v. So therefore, what is curl? Curl basically represents whether at a certain point in a vector field, the field can curl or rotate. And it is evaluated by taking the cross product of del vector with the corresponding vector point function at that point. Now I think again from your elementary knowledge of determinants and matrices and determinant, you know how to calculate the cross product between any two vectors. The simple way to calculate the cross product is, let me show it to you. For instance, suppose I have a vector, this I think all of you know this. If I have a vector which is say axi plus ayj plus azk cap, and I have another vector which is bxi plus byj plus, let's say, bzk cap. Then what is vector a cross b? This is vector a and this is vector b. So what is a cross b? It is basically the determinant. Let me erase this so that it will be easier for you to follow this. Let me choose the eraser here. Here is the eraser. So let me erase all this. Okay, fine. So that's gone. So how do I evaluate this a cross b? Well, I think you all know how to do that. A cross b would simply be this determinant. It is I, j, k cap, ax, ay, az, bx, by, bz. So if you evaluate this determinant, you get a cross b. So if you have to evaluate del cross b, what you have to do? Instead of ax, bx, instead of ax, ay, az, you have the component of the del vector, which is dou by dou x, dou by dou y, and dou by dou z, and the component of the v vector, which is vx, vy, vz. That means what is a and b here in this expression is del and v in this expression. So that is the cross product, and that this cross product is called the curl. Now you notice that you know that the cross product of two vectors is itself a vector. That I think all of you know that the cross product of a and b is a new vector c, right? So therefore we realize that when you take the dot product of del with a vector field a, you get a scalar quantity which is called the divergence. But if you take the cross product of the vector del vector a with the vector field a, you get the vector function, or rather a vector point function itself. So therefore the curl of a vector field is a vector, the divergence of a vector field is a scalar, right? So I'll go back to the pointer again so that it will be easy for me. Here is an example. Here is an example to calculate the curl. This is you must have a pencil and paper, and actually you must work this out. I've shown you the basic steps here. Now let's say you have a vector field V, and I want to show that this field is irrotational. What is irrotational? If I find that the curl of this vector V is 0 at all points in that vector field, then I would call such a field as irrotational, which means in this vector field, in whichever point I calculate the curl, I will get 0, irrespective of the values of x, y, z at that in that space or in that vector field. So here is this vector field 6xy plus z cubed I plus 3x squared minus zj plus 3xz squared minus yk cap. And the problem says that you have to show that this field is irrotational. That means the curl of this is 0 everywhere. It's very straightforward. How do I do it? I just take the curl, which is del cross V, and that is nothing but I cap, j cap, k cap, and evaluate this determinant. Here the second row is dou by dou x, dou by dou y, and dou by dou z. And the third row is nothing but the components of this vector. This is the x component, this is the y component, and this is the z component. And you can easily calculate. I will show you one of this. If you calculate this, it turns out to be 0. So let us do this. Suppose I want to calculate the first term. What do I do if I calculating the first term? I will eliminate this first column and I will eliminate this first row. Okay. And then I will take dou by dou y of 3xz squared minus y. So I need to calculate dou by dou y of 3xz squared minus y. In fact, this first one would be, the first term would be I cap into this part minus, I have to do this, which is dou by dou z of 3x squared minus z. So how much is that? That is I cap times, what is dou by dou y of this first term? Obviously there is no y, so that is 0. Dou by dou y of minus y is minus 1 minus, here I get dou by dou z of this term is 0. Dou by dou z of minus z is minus 1. And that, as you see, is 0. So therefore, that's the first term here. So let me come back to the pointer option. Let's take the pointer. the first term is 0 times I. Similarly, you can show that the second term will be 0 times j cap, and the third term will actually be 0 times k cap, right? So that means this entire curl is 0, and therefore when the curl of a vector field is 0, we call it irrotational. Okay, so that brings me to the end of the first lecture in part 1 of this course on electromagnetism. In the next lecture, I will take up specific examples of problems, numerical problems on calculating the gradient, calculating the divergence, as well as calculating the curl with certain specific examples, keeping in mind the later part of electromagnetic theory that we are going to learn. Thank you.